All right. So what is Bootstrap procedure? So Bootstrap is kind of it's also a resampling technique, but its purpose is completely different than that of cross-validation. So it is included in this lecture just because it's also resampling. So how does Bootstrap work? So let me first explain the origin of the term, right? So the original story was from 18th century. It's about this funny character called Baron Munchausen, and so there was a story about Baron Munchausen pulling himself and his horse out of a swamp by just pulling his pigtail, right? And then this story transformed into an English saying to pull oneself up by one's bootstraps. So somehow in the saying, this pigtail of Baron Munchausen was transformed to bootstrap, but the idea is the same. So it describes a seemingly impossible process where that is kind of run by internal resources, right? So what is a bootstrap? So bootstrap is this little kind of a loop on your shoe that you use to put your shoe on. Probably in modern shoes or boots, I don't think that I've ever seen it in real boots that people wear, but if you want to see it, so it's very common in, say, rollerblading. So my own inline skates, they have these bootstraps. Okay, so the analogy here is to the story with Baron Munchausen, and you will see why very soon. So here is an example from Introduction to Statistical Learning. So we have two portfolios that are random variables x and y. And suppose that the return on investment is the same, right? So it means that we have random variables x and y, and the expected value of these two random variables is the same. So expected value of x1 is the same as expected value of x2, and is some return, our returns. Right? So then we are trying to so we have some money, right? So, and we can invent the fraction alpha of our money into x and the fraction alpha of our money into y. Sorry, fraction 1 minus alpha of our money into y. And the expected value of our investment is going to be, so expected value of alpha x plus 1 minus alpha y. The expected value is linear, so this is going to be alpha expected value of x plus 1 minus alpha times expected value of y, and the expected value of x and the expected value of y are the same, so it's supposed to be alpha r plus 1 minus alpha r, which is just r. So seemingly, it doesn't matter how much of our capital we invest to x and how much we invest to y, seemingly. But it happens that although the expected return is going to be the same, there is a particular value of alpha that minimizes the variance of our portfolio, and the variance is associated with risk, right? So basically, if we know that our expected value, our expected returns are, say, 7%, it means that on average we're going to get 7% back. But of course, it is better to to be absolutely sure that it's 7% than, I don't know, than gambling. So then, I don't know, being able to get 20%, but maybe being able to lose 10%, right? So it's better to be sure. So which is why we usually want to minimize the risk, the variance. And it happens that the value of alpha that minimizes the variance is this particular number. It's just given in the textbook, but I've verified it. It's true. Yeah, I've checked it myself, and maybe I will include this into tutorial. I don't know. It's not very hard to derive. So now, but in practice, the problem is that real values, the variance of x, the variance of y, and the covariance between x and y are not known. So we have access to historical data that looks like this. So these are historical prices over the last year of stocks of CapitaLand and Singapore Airlines. Right. So this is all that we know in practice. So we have some observations and we know how they correlate. That's it. So mathematically, right? So we just have a set of numbers, like set of observations: x1, x2, x3, and so on, and set of observations y1, y2, y3, and so on. So we can construct the estimates of our variance, like to construct the estimate of variance of x. So what we do, we take 1 over in any case, you know it from statistics and probability. So how to estimate variance from a sample. So and therefore we can find this optimal estimate for the optimal value. But the question is, so we know that even if we know that it is unbiased, right? So we know that this is probably the best that we can do. How do we find the confidence interval for alpha, right? So we know if say we calculated it and found that this is 0.3, right? So it means that 30% of our stock of our capital should go into X and 70% into Y, right? But how confident are we? So is it possible that, I don't know, just because of random fluctuations in the data, because of random noise, the true value should be 0.4 instead? We don't know, right? So if we only have one sample, we don't know. So if we could generate a lot of different samples of X and Y, then we could just find this estimated alpha for each of these samples and find variance of all these estimates again, right? So again, so if this means that we could like do alpha hat for the first sample, alpha hat for the second sample, alpha hat for the third sample, and so on, right? So if we had 1,000 samples, we could do it 1,000 times, and then we could estimate the variance of our alpha hat. But in practice, this is impossible because we do not have these 1,000 different samples. So this was motivation for why we need Bootstrap. In the next remaining part, I'm going to explain the Bootstrap procedure itself. And now please do this little quiz.